Hey everyone, and welcome to this explainer. Today, we're diving deep into Amon's AI journal to uncover the absolute secret mathematical engine that's driving all modern AI. If you've ever found yourself wondering how on earth billions of parameters magically align to generate incredible art, write super complex code, or even drive cars, well, you're in the exact right place. Because when you strip away all the hype in those massive data centers, it literally all comes down to one remarkably elegant rule. So here's the million-dollar question we really need to answer. How does a neural network actually learn from its mistakes? We hear the phrase machine learning thrown around constantly, right? But what does that practically mean under the hood? Well, to truly understand how errors are corrected deep inside a massive network, our source material highlights that grasping the channeling of gradients backward through the layers is absolutely vital. Understanding this backward flow is exactly what separates true AI practitioners from the casual enthusiasts. Learning in AI is, quite literally, just error correction flowing in reverse. Okay, part one, engine of deep learning. Let's look at the motivation behind this. Moving right into section 2, unpacking the chain rule. It's time for the math foundation. All right, let's actually define the chain rule formally. Now, whether you happen to prefer Leibniz's notation, showing the change in f with respect to x through those fractional steps, or maybe Lagrange's prime notation, the core message is exactly the same. We really don't need to get bogged down in the syntax here because both of these formats are simply giving us the mathematical keys to unlock nested functions. They're telling us precisely how an ultimate output changes when we tweak an input that is hidden way, way deep inside a chain of intermediate steps. That is the secret sauce. And this concept brilliantly illustrates how we can string functions together like mathematical matryoshka dolls. Think about how those Russian nesting dolls work, one hidden inside the other. If step 1 creates our first variable y, and then step 2 takes that y to create z, and finally step 3 takes z to create our final output, we're really just nesting operations. By applying the chain rule, we can continuously multiply the derivative step by step. We're essentially unpacking those dolls one by one to see how the very first piece affects the very last piece. Section 3, Neural Networks as Functions. This is where we make the AI connection. Take a standard 3-layer dense neural network, for example, just the number 3. This means we have 3 distinct layers of computation sitting right between our raw input data and our final prediction. It sounds incredibly intimidating when we throw around big terms like artificial intelligence. But honestly, if we pause and just break down what's actually happening mathematically, it becomes so much more approachable. Because a neural network is basically just a massive, long composition of functions chained together. Think about how this equation perfectly mirrors the nesting we just talked about. Dense 3 wraps around dense 2, which wraps around dense 1. Our input data, represented by x, goes into that first layer. Then the result of that calculation passes to the second layer. And finally, that result is fed into the third output layer. So an entire neural network is really just one giant chained mathematical function. How cool is that? Next up, section 4, inside computational graphs. Let's pop the hood and look at the machinery. Let's contrast the 2 main phases of learning in these models. During the forward pass, we calculate our output using input variables. But crucially, the system caches or remembers those variables. Think of it like leaving a trail of breadcrumbs as you walk through a forest. Then the backward pass kicks in. It takes the final loss gradient, which is basically a measure of how wrong the network's guess was, and it uses those cached breadcrumbs to figure out the local gradients. It's applying the chain rule in reverse to find its way back home. The really crucial point here is dependency. Any operation in our network, whether it's adding values, multiplying them, or filtering data through a maximum gate like a ReLU, relies entirely on those variables saved during the forward pass. Without caching that data going forward, the backward pass would be flying completely blind. It'd have absolutely no local information, no breadcrumbs to compute the gradients needed to actually learn and update the model. Finally, section 5, the flow of gradients. We're calling this the relay race. I want you to picture this as a literal relay race. By receiving the upstream gradient of the loss, a node simply multiplies it by its own local partial derivative, and then it passes the baton backward to the next runner. Whether we're dealing with variable x or y, we are just using the chain rule to pass that crucial learning signal downstream, step by step, node by node, until the entire network is updated and ready to make a much better prediction the next time around. And we can distill this entire seemingly complex process into one beautiful universal rule. The downstream gradient is simply the local gradient multiplied by the upstream gradient. That's it.
That is the fundamental formula of deep learning right there. It tells every single node, no matter how ridiculously deep inside a massive network it might be hidden, exactly how it needs to adjust based on the final error. It's elegant, it's simple, and it is just incredibly powerful.
So as we wrap up this explainer, I want to leave you with a pretty incredible thought to ponder. How does this single, elegant mathematical trick, just multiplying a local gradient by an upstream gradient, scale up to train the billions and sometimes trillions of parameters in the massive AI models that are actively shaping our world today? It is simply breathtaking to realize that it's literally just basic calculus, running at an unimaginable scale, powering the future. Thanks so much for joining me on this one.